For this next unit, we're going to be taking a look at lines and planes and how they can interact with each other. Continuing with this half of the course, our definitions of these lines and planes are going to often be in terms of vectors or vector concepts. We're going to start with equations of lines in R2, which is something that you're already familiar with and from a Cartesian perspective, because you already know, for example, y equals mx plus b, the equation of a straight line. M is our slope and b is our y-intercept. Sometimes you will see this equation in the form y equals ax plus b, and it's equivalent, of course. In that case, we think of a as a scale factor, but it's a multiplier. It's the same idea. So to put this into the context of vectors, I've put together a GeoGebra page or a GeoGebra demo to illustrate this idea. So in this case, I've started with two vectors, which are the blue and the red line. And you can see that I have a purple vector that represents the vector addition of those two. So if I add the blue plus the red, I end up here at the purple. Now I'm taking this a little bit further with the idea that, well, what if I scale this red value? And here's my scale factor. T is equal to 1 right now. So that's why this dotted red line, which is just the same as the red vector, they're both the same length. But if I were to double that, you can see it's still along the same direction as the red vector would be, but now it's twice as far. But in doing that, I have described a new purple vector, a new resultant vector, and we can think of the point on the end of that resultant vector as being, this is the point that we're interested in. So now I want you to focus your attention on that point. And in doing so, I think the other thing I will do there, if I can get it to come up, is I'm going to turn on the trace for that point. And you can see that depending on the scale factor that I choose, it's actually going to describe a whole set of points. And those points, as you can see clearly from here, those points describe a straight line. And so this is getting into the idea of a vector definition of a line. This purple line can be defined in terms of some starting point, and that starting point is defined by some initial vector. And then the rest of the line is basically moving by another vector, but that vector is described by a scale factor. Now that may be a lot to process verbally, so I'm not going to, of course, leave it there. I'm going to, first of all, show you what the vector equation of a straight line is. And down here I have an illustration where I've tried to capture more or less what I showed you on the GeoGebra page. So the position of any point, again, I've got this purple line. The position of any point along this purple line can be described in terms of a starting position, which we find by following an initial vector. So that's what I've got here in blue. And then I have a direction vector, which I'm using the symbol M for, and that's not an accident. I'm using the same symbol that we use for slope because it turns out that this vector has properties that are related to the slope of this vector. And then t is our scale factor, and that's just how much do I want to scale this red vector to go find the various points that I did along this line. So if t is equal to 0, for example, we're just at the end of the blue vector. And then I can extend in either direction. So let's do an example where we try to put this into practice. So we have a line that passes through the point 5, negative 2, and it has a direction vector 4, 6. So I think I might just go ahead and give a very quick sketch of this just off to the side. Nothing too detailed, but the point 5, negative 2, so there's my starting point, which means my starting vector looks like that. My direction vector is 4, 6. So my direction vector looks something like that. And so that means that I'm going to, from this starting point, I'm going to follow that direction vector. So it's going to be this blue vector, maybe plus a small amount of that direction vector, or it could be plus a large amount of that direction vector. So I'm going to end up with a line described by these various points. And so I'm going to end up with something like that. That's going to be the straight line that I'm describing. What we've been asked to do here, though, is to state the vector equation of this line. So the vector equation, the typical form for the vector equation is we write it as the vector equation, or the vector, is equal to the initial vector, or the starting point, plus a scale factor multiplied by the direction vector. In this case, our starting point is at 5, 2. So that means if our starting point is at 5, 2, or sorry, 5, negative 2, then that means that there is a vector that we could describe which goes to that starting point from the origin, and we are setting that to be our initial vector, r0. So that r0 in component form is 5, negative 2. The scale factor can be any number, t, and our direction vector is already given to us. The direction vector is 4, 6. And you don't need to do this every time. Actually, you know what? You do need to do this every time. You really do need to say that t is a value in the reals. And the reason why I changed my mind there is because there may be situations where you actually end up restricting t for some reason or another. So if it is unrestricted, then you really need to make that statement. So there is my answer to A. Part B, find the point that corresponds with t equal 3. So if I let t equal 3, then I get r is equal to 5, negative 2, plus, but in this case it's going to be, I'm going to substitute 3 in for t, times the vector 4, 6. That's the vector 5, negative 2, plus 3 times 4, 6 becomes the vector 12, 18. And so we end up with 5 plus 12 is 17, and negative 2 plus 18 is 16. And since this is the vector to the point, so therefore the point is, I'm going to call that Q, 17, 16. I don't really even need to give it a label. I just want to make it clear that there's a difference between a vector and a point here. It's a subtle difference. The numbers look the same, but there is a difference. Part C, does the point 1, negative 6 lie along this line? Now, my graph isn't terrible here, so 1, negative 6 down here somewhere. Does that actually lie on the line, or is it off to the side? So I've given myself a little bit more room to move to the next page. So does the point 1, negative 6 lie on this line? So here was our vector equation of the line. And what we want to know, essentially, if the point 1, negative 6 lies on this line, then that's another way of saying, does the vector r equal 1, negative 6 touch the line? So if we go from the origin to this point, does that vector satisfy this equation? So we say 1, negative 6 equals 5, negative 2 plus t times 4, 6. And now I have to solve this equation. And the best way to solve this equation is to break it out into its x and y components. And so I get 1 is equal to 5 plus 4t, and I get negative 6 is equal to negative 2 plus 6t. And I have two equations here, and I have to make sure that it actually works for both of these equations. And so which one looks easier to solve? They're both pretty much the same. Actually, no, this first one, if I call that equation 1, call that equation 2, this first one looks a little simpler. I get negative 4 is equal to 4t, and I get t equals negative 1. And now I have to check. Well, actually, I could check t equals negative 1, or I could solve for t. So if I check t equals negative 1, I get left side equals negative 6, right side equals negative 2 plus 6 times negative 1, which is equal to negative 2 minus 8, minus 6. And the overall is equal to negative 8. Or I could do this one, which means I take this negative 2 over to the other side, and I get negative 4 when I add 2 to both sides equals 6t, and I get t is equal to negative 2 over negative 4 over 6. I'm jumping ahead in some of my arithmetic here because this ends up being negative 2 over 3. Now, in either case, what we have here is an inconsistency. We either say it's failed our left side, right side check, left side is not equal to right side, or we end up with two t values, and that's not possible. So since I have an inconsistency, therefore, and what was that point? 1, negative 6. Does not lie on the line. And finally, write the equation in the form y equals mx plus b. So let me just grab a hold of that equation, copy it. I'm going to create a new page, and I'll paste it into there. Okay, so now we want this. This is not part A, this is part D. In the form y equals mx plus b. In order to do this, we're going to focus on our direction vector, which is 4, 6. And that direction vector being 4, 6, if I just sketch that out, what does that mean to have a direction vector of 4, 6? That means go to the right by 4 and go up by 6, and we end up with the direction vector there. But what is the slope of this? Well, we know that slope, on the other hand, is defined as the change in y over the change in x, which in this case we went up 6 units and across 4 units. So that gives us a slope of 3 over 2. But the important part is this line where we wrote 6 over 4. Notice that that matches our x and y coordinates. If we think of our for our direction vector, if we think of our delta x and delta y, not just x and y, but delta x and delta y, we get the slope. So that means my equation is actually y equals 3/2 x plus b. And then from there, we could sub any point that we know does lie on the line. And we should know that. Oh, actually, I don't need to go back here for that because we have it right here. We're going to sub the point P naught, which comes from R naught. So we know the point 5, -2 lies on the line. So I get -2 equals 3/2 times 5 plus b. We're going to solve for this y-intercept now. So I get -2 equals 15/2 plus b. And I'm going to need a common denominator, so I'm just going to go ahead and change this to -4/2 minus 15/2 is equal to b. And I end up with b is equal to -19/2. And so from there, my equation of my straight line is 3/2 x minus 19/2. Now, parametric equations are actually something we've dealt with to a certain extent because we've been making use of the idea of components to solve, for example, if we were trying to solve for a spanning set, if we were trying to show that one vector could be written as a linear combination of other vectors. It's a fairly common strategy that we've used where if we have a vector equation, such as the one I have written here, we pull out the x component, and the x component on the left of the equal sign must be equal to the sum of the x components on the right. And that's what I've got written here. This x must be equal to the initial x plus t times a, which I've written as at. This y must be equal to the initial y plus t times b, which I've written as bt. And that's it. These are your parametric equations. So in R2, so we get 2 parametric equations in R2, and as you can imagine, if we were in R3, we will be getting 3 parametric equations. And the parametric form can be more convenient for solving. In the previous question, we ended up having to split into essentially our parametric equations just to solve the system of equations anyway. So it's actually a very convenient form. So for exercise 2, find the vector and parametric equations of the line passing through the point M57 and N82. So M57, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So there's the point M. N is 8, 2. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. And that's N. So that means I have, for example, I have vectors to each of those locations, but I also know my line. First of all, my line lies between those 2 points. So my line looks like that. And so what I actually need is my direction vector. My direction vector is the vector between M and N. Now I could use my direction vector could be, and this is capital M, capital N, it's the vector between them, or I could set my direction vector equal to capital N times capital M. Both of those would be fine. I'm choosing, I'll just go alphabetically, and so I'm going to use this one. And in this case, my direction vector, well, the vector Mn is defined as the vector On from the origin to N minus the vector from the origin to M. And On is 8, 2 minus OM, which is 5, 7. 8 minus 5 is 3. 2 minus 7 is -5. So there we go. We have our direction vector. This direction vector applies for this entire red line. For our vector equation, just to remind you again, till you get used to it, our vector equation is written in terms of the initial position vector plus a scale factor times the direction vector. Our initial position vector, well, we actually have two potential initial positions. So for this one, I could use OM or ON. Either of those are valid initial positions. Again, just alphabetically, I'm going to go ahead and use OM. So I'm going to use this one, and I end up with R is equal to OM is 5,7 plus T times 3 negative 5. Find the vector and parametric equations. So I have the vector equation. That's what I have found so far. For the parametric equation, all I need to do is, it might be worth it to write this in another form, which is that this is the x and y component of the resultant vector is equal to the x and y component of the initial vector plus a scale factor times the x and y component of the direction vector. And so my parametric equations, I take the x component of the resultant vector is equal to the x component of the initial vector plus the scale factor times the x component of the direction vector. And you can see why in the previous slide I changed the order of these, because we don't normally write T3, we write 3T. So that's my parametric equation for my x direction, and then my y direction is going to be 7 minus 5t. And so here is my vector equation, and here are my parametric equations. Now there was a second part to this question. It said find two vector equations perpendicular to your answer from part A. So here is my vector equation from part A. We want to find two vector equations which are perpendicular. Now when we talk about perpendicular, the concept that we've talked about in the past when we talk about perpendicular is usually slope. So it actually makes sense here. What I should do is figure out what is the slope of my line. And to find the slope of your line, remember that your direction vector can be thought of as delta x. The x component is the delta x, the y component is the delta y. So slope is defined as delta y over delta x. So that's going to be negative 5 over 3. But we're not interested in this slope. We are interested in the perpendicular slope. And that's going to be equal to the negative reciprocal of this, which is positive 3 over 5. So this slope leads me to this perpendicular slope, which leads me to my perpendicular direction vector, and that is going to be equal to, when I write this, don't forget I'm writing this as delta x and delta y. So my change in x is actually equal to 5, and my change in y is equal to 3, because don't forget that's delta y over delta x. So there is my perpendicular slope. And so the line that is perpendicular to my original line is going to still has to pass through this point. So we use the same initial vector plus t times 5, 3, which is our perpendicular. Let me go back here just before I fill that in that way. And then I'm just going to make a little note here that this is still the same starting vector. Okay, because we have to be perpendicular. Actually, do we need to go through the same starting point? We do not need to go through the same starting point. Let's go back to our diagram just to illustrate that. We could go through the same starting point, which would give us a line like that. That's perpendicular. But we could also go through the point N, and we could go through any number of other points. So it turns out what I just put there was valid. So this would be correct, but I could also say, or R perpendicular equals, and let's go ahead and go through N. I could go through N, 8, 2, plus T times M perpendicular, which is 5, 3. And up here I should have also written another line, but I'll just go ahead and replace that. So this is now the point N, or in general, R perpendicular is equal to any point AB plus T 5, 3, or any starting vector. So any start is valid, and the direction vector must be perpendicular. That's the important part, is that the direction vector is perpendicular. But you can see that any starting point is valid. And now you might ask the question, well, hold on, don't you at least have to make sure that starting point is on the line? And the answer to that is no. I could actually choose my starting point to be here. So that's just some random arbitrary starting point. But can I draw a line through that point that is also perpendicular to this red line? I absolutely can. So it's the direction vector that ends up mattering. And I believe that's it. So there we have two specific vectors that are perpendicular, and then a generic vector that is perpendicular. And that's it for this lesson. Really just a repackaging of concepts that you've already seen and you've already worked with before. It's just a matter of organizing them in a slightly different way.